we will solve again problem which we discussed in the past. What happens, I mean, how to analyze a motion of an object. And I took an object, I model it with these two balls, thinking of each ball that it's a particle. So this is an object which has two systems. And I want this object to move like that. So we will use now all versions of Newton's second law and all versions of work energy theorem to analyze it. Will be 8 different solutions. Obviously, the conclusions has to be the same, right? It behaves like it behaves. Now, it's kind of blessing that we have so many theorems, but at the same time, it's a curse. Because if you confuse one solution with another, take part of the solution from one approach, part of the solution from the second approach, the solution will be wrong. You have to be consistent. And really this is what at this moment probably makes the subject, physics, difficult. That you already know too much. In principle, you have too many tools, you don't know which one to pick. All right. So, actually, the first solution which I'm going to so how about if we phrase the problem? So let's say I have two balls. One is going to drop, let's say from height distance. It is much better actually to look at the algebraic solutions than numerical, because with numerical solutions, if you get the same results, it doesn't guarantee that really the solution is correct. It would be maybe coincidence. If the expressions, algebraic expressions, are identical, then we know that the solutions are identical as well. And let's say that our question is, with what speed this ball is going to hit the floor? So what is, let's call it that this is particle 1, this is particle 2, and we want to find speed of particle 2 when it hits the floor. I will call it final. Initial is when it was released. And I release it from with 0 velocity. Now, if we look at chapter number 2 or chapter number 4, when we discuss kinematics without really analyzing why does it happen, we would be already able to solve this equation, this problem. How about if I introduce coordinate system in such a way that the down is x, and y and z are horizontal. So, based on chapter number 4, what will be the speed of the ball over here? How we would solve it? Actually, this solution is based on Newton's second law. I just want to bring it up so that we recognize what to do. I wanted to use Newton's second law first to predict motion. And could you remind me under what circumstances Newton's second law gives advantage over work energy theorem and vice versa? When we are concerned with time, it's better to use Newton's second law. If we are concerned with positions, then it's better to use work energy theorem. So with that information, for example, which we have right now on the whiteboard, it would be better to use work energy theorem or Newton's second law. Just figure out, do we have time information or position information? Position information, which means work energy theorem is more convenient. Although, as I said, we can solve it Newton's second law as well, because now we can easily convert it into time dependence. Yeah, let's say that I release it at t equals 0 seconds when the ball is going to be here. Well, we believe that this motion is a motion with constant acceleration, So we remember that for constant acceleration, position is a quadratic function of time. Right now, here initial, let's say that I also put origin over here. So initial position is going to be 0, initial velocity is going to be 0, so we'll have only vertical component which depends on time. And well, I can write down an equation that h is equal to acceleration times square of speed over 2. So from that I find that time is equal to square root of 2h over g, right? So now I convert it to time dependence. I know now I know at in what time, what instant I'm interested. So if I already know this information, I can solve problem using Newton's second law. All right, let's now start talking about Newton's second law. So the first version of Newton's second law. Can we refresh? Consult with your neighbor to recall Newton's second law. And how about if somebody says it in an approximate way? Can you say it in an approximate way, and then we will fix it up?
Okay. The net force acting on an object is
not object. This is particle.
Is equal to the mass of the particle.
Correct.
Acceleration experiences.
Correct. What is missing? In an inertial reference frame. Don't forget about inertiality of the reference frame. All right. The classroom is pretty good inertial reference frame, so that ball, the motion of that ball was observed in an inertial reference frame. Good. All right. How can we apply now to the problem? Can we now use the object and use this version of Newton's second law? Who votes yes? Who votes no? Those who vote no, you are right, because this system is an object. Well, however, each of the components of the system is a particle. So I can separately now use Newton's second law for each particle. All right. So for particle 1, I have that the net force is going to be 0. I look at the configuration. When I'm holding it, how the free body diagram looks like. What forces are exerted on particle 1? Gravitational force exerted by the Earth. And, well, if I held it that way, then it would be support force. If I hold it that way, it will be static frictional force. But one or the other types of interaction with me, right? So I'll mark it, let's call it support force, normal. Now from that configuration over here, I recognize that the two forces must cancel each other out. The object does not accelerate, right? So obviously its acceleration is going to be 0. If acceleration is 0, what happens with velocity? Stays 0, correct. So this particle stays in place. Now, if we apply the same thing now for this particle, when it is falling, if I mark it somewhere in the air over here, let's identify forces on that falling ball. Can you help me with that? Gravitational force exerted by the Earth on? Good. All right. Now it's identical as this one. Right? I can write actually this is mass times acceleration due to gravity. What else? Consistently with that other one. Who exerts it? How? No. We are talking about when it is in flight, before it hits the ground. No other force, correct. This is the only force exerted on that ball, which means that the net force is equal to the gravitational force. All right. Now, from Newton's second law, therefore, I can write out that mass of this particle. And how about if I concentrate just on the x component? So I'm thinking only about x component, because all the others are 0. So I don't write vectors now. So mass times acceleration of the particle is equal to the weight of the particle. Mass times acceleration due to gravity. Should I put minus here? Why not? Because I picked axis down, right? If I had axis up, then I would have to be consistent and put minus over here. I choose coordinate system in such a way that now it's positive. So from that, I figure out that acceleration is equal to acceleration of a particle at any instant, no matter where it was, is equal to acceleration due to gravity. Well, therefore, speed of the particle at this location is equal to initial velocity, magnitude of initial velocity, which was 0, plus acceleration times time from here to here. So it will be g times t. And, well, since time was not given at the very beginning, but the height, well, I find now that time was related to height in that way. So I have to put it over here. And if I multiply g and this expression, I will get square root of 2gh. Yeah, we figured out speed of second particle over here. All right, what was the second version of Newton's second law? Refresh my memory about second version of Newton's second law. This was solution based on the first law, first version of Newton's second law. And second version of Newton's second law, somebody maybe can help me. Can you? Okay.
In an inertial reference frame, the rate of change in the momentum of a particle is equal to the net force exerted on the particle?
Correct. Right. Yeah, so in the second version, we had that rate of change in momentum of the particle was equal to the net force exerted on the particle. All right, so if I know rate of change, then I can find out what is the change from the top, from this location to this location. Yeah, from this expression, I can quickly write down that differential change is equal to net force multiplied by differential time and integrated from initial momentum to final momentum. So over here I will integrate it from initial instant to final instant. On the left hand side I will have change in momentum. On the right hand side I will have net impulse. Really, we have the solution goes through the derivation of impulse momentum theorem. All right, so let's now concentrate on x component of momentum. What is momentum over here? It's mass of that particle multiplied by final speed of the final component of velocity of the particle, which happens to be equal to speed, minus now initial momentum when it was here was 0. So minus 0. And this is supposed to be equal to that impulse, to this integral. Actually, probably it's even better not to, this was a digression. Really, this one is more useful for me. Because now I have to integrate from initial instant to final instant force. And x component of this force is going to be mg times dt. So I get over here that this is mg t final minus t. This one is 0. This one is our t. So it's mg t. Well, now I can divide both sides by m, and I get that final speed is acceleration due to gravity times t, and t is equal this much, so I'm getting that it's not this much. T is this much, so I'm getting 2gh. Is it okay? Consult with each other if this result makes sense now. Does it make us happy? Who is happy? Why are you happy? It's the same. What is the same? The conclusion is the same. Yeah, speed of particle 2 when it hit the floor is 2 times acceleration due to gravity times the height from which it was released. Over here it is also 2, square root of 2 times acceleration due to gravity times height from which it was released. All right, we have a question or a comment. Can you say it?
I just want to know, so are those two solutions basically showing that two versions of Newton's second law work the same?
Correct. Yeah, and we are going now to use two more versions of Newton's second law and also come to the conclusion that the result is the same. I mean, I hope that it is not too boring, yeah, because we are all the time we are getting the same result. But I really want you to see the differences. Yeah, I want you really to recognize, so you don't say anymore that F equals ma or force equals mass times acceleration. You have to know what is what of what in everything. All right. What was the third version of Newton's second law? Anybody remembers? Jessica, do you remember? Third version of Newton's second law. We need it urgently. It was also with momentum. Have you found it? Mark, have you? Oh, you got it? Okay. Say it.
In an inertial reference frame, total momentum of an object is equal to the total net external force exerted on the system. Is that one we already used?
This is the one which we are going to use now.
Oh, okay.
Yes. So that in an inertial reference frame, rate of change of the total momentum of the object is equal to the net external force exerted on the object. How about if I write it down then? As this is third solution, this time we are using that the rate of change in the total momentum is equal to mass of the object, not mass of the object, is equal to the net external force. Now, what is that P? Can you remind me what is P? What momentum of the object? What momentum of the object? What do we mean by that? Total momentum, right? So this is sum of the momenta. Now we can either it's over here when we calculate when we consider total momentum, we can indeed add momenta of the two particles. Well, because this is a two-particle system. Well, very few objects are two-particle system. I am not a two-particle system. So usually when we consider total momentum, we use a certain theorem, how total momentum is related to certain velocity. Which velocity and how? Total momentum of the system is associated with a certain velocity of the system. Velocity of center of mass, correct. So total momentum of the system is equal to the product of mass of the total mass of the object multiplied by the velocity of the center of mass. All right. Actually, Now, this calculation will be very similar to that one. Yes, so first thing which I'm going to do is I recognize that differential change in the total momentum of the system, is equal to net external force multiplied by differential time. Now I will integrate this expression for over the period of time in which things happen, so from t initial to t final, which will give me that. What is that? Change in total momentum of the system, correct? And then we'll have integral over here from t initial to t final. We can also recognize that this is net external impulse exerted or delivered to the system. All right. Now we decided to take advantage of of a theorem which relates velocity of center of mass with momentum. So, well, center of mass is somewhere. I mean, these are two identical balls, so it's halfway between. If this particle here has a certain velocity, compare velocity of center of mass if the other particle doesn't move. Half, correct. So velocity of center of mass is half of the velocity of the particle. So now, change in total momentum, I will take total mass of the object. What is the total mass of the object now? 2 times m, right? Because 2 times m, because we have two particles. Multiply by, I'm considering just x component again, so x component of velocity of center of mass is going to be half of this velocity. This is momentum at that point. So it's final momentum. Now I have to final total momentum. Now I have to subtract initial total momentum. What was initial total momentum when the particle was here? It was 0, correct. So we got change in total momentum, and this one is supposed to be equal to integral from t initial to t final. And let's now find out from what. What do I have to add now? Net external force. So what should I write over here? Net external force. All right. So we have gravitational force exerted on this particle plus the normal force exerted on that particle. That one actually happens to be minus mg, right? It's opposite. So it is minus mg, and this is force exerted, x component of the force exerted on the left-hand side particle. On the right-hand side particle, I will have just mg dt. Let's integrate that. So this is 0. Here we have mg. Mg is a constant. I can take it in front of the integral and integrate just dt. So it will be change in time, right? So it will be mg times change in time. So it was t minus 0, so it will be t. So now, I see that 2 and 2 cancels here. Now I have m over here and m over here, so I can divide both sides by that, and I will get that speed of particle 2 is g times t, which is equal, and I plug in again at what instant the ball hits the ground. So I'm going to get square root of 2gh. Are you happy? Why? It's the same, right? We got the same. Now, do you see the difference in the solution? I mean, kind of a trivial solution. So I'm taking a force which is easy to integrate. One particle does not move, so this cancels out. But I want you to see those procedures. What was the difference? All right. What was the fourth version of Newton's second law? Look quickly through your notes. Whoever finds it first, grab the microphone. Did you get it, Chris? Okay, we got it. Have you heard it? I think she didn't shout enough. Let me shout what she repeat what she said. In an inertial reference frame, the acceleration of the center of mass of the system is proportional to the net external force exerted on the system. All right. So it says that acceleration of the center of mass of the system, which means that this acceleration of this point, acceleration of the center of mass of that point is proportional to the net external force. And the proportionality coefficient is mass, total mass of the system. All right. So let's figure out what is the acceleration of the center of mass of this system. And actually, we even know. I mean, yeah, because I mean, even if before we find it, we know from chapter number 4, in fact, that that this point is always between this one and that one. So this velocity is always half of that one, which means that the acceleration should be also half of the acceleration of that other particle. Well, let's see if we can conclude it from Newton's second law. So acceleration of the center of mass is, this is again x component, just that vertical component down, will be 1 over total mass of the system. What is total mass of the system? Can you help me? What is total mass of the system? 2m. And now we have to write expression for the net external force. What do I have to add? mg minus mg, correct? Yeah, because these two together are combined into the force exerted on particle number 1, plus mg, because this one is the force exerted on particle number 2. What else? That's it. Correct. That's it. So here we have acceleration of the center of mass. Well, if I simplify this expression now, I will get that it is g over 2. Is it good? That's good, right? That's good. I mean, we just predicted a moment ago that acceleration will be of the center of mass is going to be half of the acceleration due to gravity. All right. So now let's find out what is the speed of center of mass, or vertical component of velocity of center of mass at the instant when this ball hits the floor, and then I will just multiply by 2 and get that speed. Do you understand me? So speed of the center of mass, now from this expression, its initial speed of the center of mass, which was 0, plus integral from t initial to t final of acceleration. Accelerations happen to be g over 2 times dt. So if I integrate that, I will get 1/2 g times t. And t is over there, so I will get that this is 1/2 square root of 2gh. Am I happy? Are you happy? I'm not. I mean, I still didn't calculate what I needed to. What are we calculating? We're trying to, in each problem, we're trying to find the same quantity, speed of particle 2. So now, what is the speed of particle 2? Twice the speed of the center of mass. Well, so if I multiply 2 by this expression, I will get square root of 2gh. And now I'm happy. Right? Are you? Yeah. Good. Yeah, because it's a fourth solution and we still got the same answer. Right. So this covers all versions of Newton's second law. Now let's take a look at work energy theorem. I have to erase part of it. Why don't you, in the meantime, why don't you look for the first version of work energy theorem? Anybody found it? Have you? Who found the first version of work energy theorem? You found it, okay.
All right, in an inertial reference frame, the work done on all forces exerted on the particle, the net force is equal to the change in kinetic energy of the particle.
All right, yeah, if you read it, the two alternative phrases for net work or work done by the net by all forces, it is kind of confusing, but that's okay. We can say that the work due to the net force exerted on the system of particles is equal to the, not system of work done by the net force on the particle is equal to the change in kinetic energy of the particle. How can we apply it now to this problem? Why don't you now discuss with each other how can we apply this version of work energy theorem to this problem? How would you do it? Well, just look at, I mean, do we have particles over here? Yes, we are actually interested in one of them, right? Which one? The 2, right? So let's ignore particle 1 and concentrate on particle 2 and find out what will be the speed of that particle. So if I just observe particle number 2, net work done on particle 2 is equal to change in kinetic energy of that particle. All right. So let's start with the change in kinetic energy in terms of this final component, final velocity. So it will be mass of the particle times square of the speed of the particle over there. Now, because other two components of velocity are 0, so speed is equal to this component of velocity. So I will have final component of velocity of particle 2 squared divided by 2. This is an expression for kinetic energy at that point in terms of the unknown component of velocity. Now I have to, in order to find change, I have to subtract kinetic energy which it had over there. What was kinetic energy over there? 0. And this is supposed to be equal to the work due to the net force exerted on the particle. What is the net force exerted on the particle? Just equal to the gravitational force, right? There's only one force exerted. So that the work due to gravity is the net work. Now we can use the definition of potential energy and subtract potential energies. And so let's say that I will assign potential energy over here to be 0. Potential energy over there would be therefore mgh. So so the change in potential energy is going to be minus mgh, and work is gravitational work is opposite to the change in potential energy, so work will be mgh. So I see that m and m cancels. If I multiply both sides by 2 and take square root, I will get final speed as square root of 2gh. Isn't it amazing? It's a fifth solution which leads to the same answer. We are really good. If we got 2 different answers, it means that we messed up something. Taylor has a comment or question.
Did you say that the reason it's not negative is because the force is in the same direction as the displacement?
Actually, I didn't. However, this is a good argument. Yeah, because now we can calculate the gravitational work 2 different ways. One way was directly from the definition, that and particularly that force is constant. So if we integrate, the result will be scalar product of force and displacement. And now force is down, displacement is down. So scalar product of those 2 is going to be positive. So magnitude of the force is mg. Magnitude of displacement is h. And then I have to multiply by cosine of 0 degrees. So work is mgh. I didn't do it that way. Yeah, because for conservative interactions, I don't want to use, I want to avoid actually calculating work directly from definition, because in principle it's integration. It's always integration. It happened so easy over here because force was constant, so it's trivial to integrate it. But for conservative interaction, we'd rather use concept of potential energy. And according to definition of potential energy, work from one location to another location is opposite to the change in potential energy. All right, so I could calculate this gravitational work as opposite to the change in potential energy. I copy opposite. Now, let's say I pick the reference for potential energy at the bottom. So final potential energy would be 0. Initial potential energy will be mgh. So this minus cancels with this minus, mgh. No matter how we calculate it, is it crystal clear to everybody? Great. This was a digression, though. Let's now go to the next version of work energy theorem. What was the next version of work energy theorem? Well, let me help you then. It was the change in mechanical energy is equal to non-conservative work. Change in mechanical energy of a particle is equal to the non-conservative work done on a particle. All right, we have one interaction over here. Gravitational. Is gravitational interaction conservative or not? Yes, we have concept of potential energy for for gravitational interaction. All right, so change in mechanical energy, well, it means change in kinetic, well, kinetic energy over here is going to be mass of the particle times speed at that location squared over 2. What is potential energy of the particle there? 0. Correct. So this gives me mechanical energy of the particle over here. Now I have to subtract mechanical energy over there. Kinetic energy over there was 0. Potential energy over there was mgh. This is change in mechanical energy. It is supposed to be equal to the work due to all interactions which we have not included in the potential energy. What did we not include in potential energy? In other words, let's calculate. Yes, what I'm saying? What have we not included in potential energy? Nothing. Everything. Yeah, we have only one interaction, one force exerted on the particle, and it happened to be conservative. We took gravitational interaction into potential energy, so what was left is nothing. There is no interaction, other interactions. So how much non-conservative work is done on the particle? 0. Right. Okay. Good. Yeah. So from that, I mean, 0 doesn't matter here, doesn't matter here. I will move now this term to the right-hand side. Well, here we have minus mgh over here. I move it to the right side. Well, first of all, let's divide by m. Yeah, so from here, I will get that the speed is square root of 2gh. Again, the same thing. Let's now go to the next version of work energy theorem. What was the next version? Well, let me remind you now. It was for translational motion. Change in translational kinetic energy of the system is supposed to be equal to the net external work done on the system. On the center of mass of the system. Right. So, what is translational kinetic energy of the system when the ball is over here? We have to take mass of this entire object. So this is 2 times m times, well, let's say square of a speed divided by 2. What's square of what speed? Center of mass, which happens to be half of that speed. So this is final translational kinetic energy of the system. Now I have to subtract initial translational kinetic energy. What is initial translational kinetic energy of the system? 0. And it is supposed to be equal to which work? Network. Yeah, so now all forces are conservative. Oh, how about if I write it? Yeah, so this is integral from initial location to final location of, and now what are we going to have as the force? Well, what do I have to add now over here? mg minus mg. This is the force exerted on the first particle. What else? Plus mg. Actually, how about if I write down, since x is our variable of integration, I can write down that this is from 0 to h. So it will give me, oh no, it isn't from 0 to h. It's from 0 to, not negative h. No, down is positive. But h is from here to here. Now we are calculating work done on the center of mass. 1/2 h, correct, to h over 2. So over here I will get mg h over 2. All right. Well, 2 and 2 cancels here. M and M cancels there. So here I have V2 final square over 4 is equal to GH over 2. So if I multiply both sides by 4 and take square root, I will get square root of 2H or 2GH. Unfortunately, I don't have time for the last version, so how about if you really work it out, and tomorrow I want somebody to come to the whiteboard and solve it, okay? So solve this problem just one more time. Now this time using the fourth version of work energy theorem, which says what? That the change in the total kinetic energy is equal to the work done by all forces on the points where they are applied. All right? See you tomorrow then.